we will be doing more examples of implicit differentiation. Before we get back to that, we're going to take a little bit of a detour into inverse trig. It may seem like this has no connection at all, but it turns out that we're going to be able to use the technique of implicit differentiation to find the derivatives of our inverse trig functions. So we're going to go ahead and do that, and then we'll return and do some more examples of implicit differentiation in general, but incorporate the new formulas for the inverse trig functions. So before we do that, I'm going to do a very quick review of some inverse trig. I will just remind you that in the materials, the video lectures that are posted as additional resources for trig, there are videos going over inverse trig if that's something that you feel like you want to review more. Now I'm going to just start with a trig function. Let's start with y equals sine of x. And clearly this function is not invertible, because in order to be invertible, a function has to pass the horizontal line test. A horizontal line would pick out every point on the plane that has a particular y value, and I can see that this crosses any horizontal line between height -1 and 1 infinitely many times. And in fact, because all trig functions are periodic and they do their thing and then repeat it, no trig function is invertible. So you would think that would be the end of the story and we wouldn't have these things called inverse trig functions. But we do. What we do is we say, let's create a related function. It's going to be y equals sine x, but with some restrictions on x. I'm going to restrict the domain so that I look at just part of this graph, a part that is in fact one-to-one, that passes the horizontal line test so it's invertible, and I'll take the inverse of that. Okay, so as we do that, we basically want to take an interval along our x-axis that would correspond to 2 quadrants worth of angles. When we're graphing our trig functions, we represent the angles on the x-axis, so that the angle increasing just means that we're moving to the right. But we also know that we can represent angles rotationally, like so. When I do that, this would be 0 and this would be pi over 2. Okay, so that this interval between 0 and pi over 2 actually corresponds to angles that are in quadrant 1. Okay. And of course we rotate around, so we go 1, 2, 3, 4. Over here, from 2 pi to 5 pi over 2, we'd be back in quadrant 1. But one rule for restricting the domain of our trig function to define our inverse trig functions is that we're always going to choose the standard copy of quadrant 1. So we're always going to choose this interval from 0 to pi over 2. That gives us our acute angles. Those are the nicest angles to work with, I think, because then we can use right triangle trigonometry. Okay. Now, with that, we've chosen quadrant 1. Okay. I would like to get just one interval. I want to get also the places where sine takes on its negative values. Okay. And I'd like to get a nice connected interval. I don't want to jump to way over here to get my negative values. I'd like to get a negative piece that's attached to that. And it looks like if I want a connected piece of graph, I want to follow this down to negative pi over 2. Okay. So it looks like that's the part of the graph that I'm going to want to keep, like so, going from negative pi over 2 to positive pi over 2. Okay. This is 1-to-1. So this is y equals sine x with x in the interval from negative pi over 2 to positive pi over 2. Notice, thinking in terms of quadrants, in order to get a connected piece of graph, I want to make sure I'm not choosing quadrant 3, I'm choosing one of my adjacent quadrants. But I couldn't choose quadrant 2 because in quadrant 2 sine is positive. So we restrict the domain to this interval from negative pi over 2 to positive pi over 2, which corresponds to quadrants 1 and 4. And then we can take the inverse of that function. So we're going to call it inverse sine, but that's kind of a misnomer because it's not the inverse of sine, it's the inverse of this function right here. So what we're going to have is y equals arcsine of x, which is the same as sine inverse of x. Either form of notation is okay. I prefer this for two reasons. One, a lot of times people confuse that with an exponent. That is not an exponent, it's an inverse sine. If I meant the reciprocal of sine, I would either write 1 over sine x, or I would write cosecant. This is inverse sine or arcsine. I prefer that. I have three reasons for preferring it. Okay. I get the inverse function by reversing the roles of x and y. So this is going to become x equals sine y, and y is in the interval from negative pi over 2 to pi over 2. Okay. So what that's doing then is that makes y the angle. And the radian measure of an angle is related to its arc, the arc length that's intersected by the circle. So having that word arc in there helps me to remember that the output is an angle, because I'm so used to the angle being the input in my trig functions, but it becomes the output in my inverse trig functions. The third reason I like arcsine is because it's, when you say it, you say r, okay? And that helps me to remember that I'm working with the restricted domain. It's not the inverse of sine, it's the inverse of sine with a restricted domain. Unfortunately, this function doesn't have a special name. It's just sine with the restricted domain. But that's the function that we're taking the inverse of. Okay. So if I have y equals arcsine of x, that means x is equal to sine y, and y is in this interval. Okay. You can say that in words. Y equals arcsine of x means that y is the angle in this interval whose sine is x. And it's that restriction that makes this a function. If I just said y is the angle whose sine is x, it wouldn't be a function, because let's say x was 1/2. Sine of y equals 1/2 has infinitely many solutions. But sine of y equals 1/2 in this interval only has one solution. So that gives us a unique output for each input. Okay. All right. So that's how we define arcsine. That's a very quick run through of that. But notice what that does is right now, if I wanted to take the derivative of this, given it in explicit form, I don't know that yet. Okay. But here, this implicitly defines that relationship. Okay. I've got y plugged into sine. I can use implicit differentiation to try to figure out the derivative of y, which is arcsine of x. And so that's what we'll do in the next video.